Suerte que tenemos la pena. Mario Cosenza comes in physics in Caracas, in Venezuela. Not now, with the gravitational. Austin, where he was working at that time with Canada, where he was working with subjects, his keywords in Google Scholar account. Gordon Prize in science in Mérida, and this is true, he's known as the he visited us many times, and there are a pleasure to have you again here, Mario. Well, I am very grateful. A world-class institute after this. Where I will show some of the
in recent years, name that is chimeras or the chimera was a monstrous part of a goat. Appears is common in the and is of course a these things. So the name chimera word chimera refers to an organism that contains this is an example. This is a I don't know if you can see it, but this eye is red. Temporal dynamical systems, a chimera the synchronized or incoherent regions or system in different parts of the system. And where they long-range coupling, you see the coupling and what they observe for some parameter is that the system spontaneously segregates into two groups or subsets. Oscillators are synchronized, that is their state variables are the same at a given time. And the other subset contains desynchronized elements. Their states are different. And here there is a snapshot of the state of the system in this situation. You see, here are the spatial index of the oscillator, and this is the phase. And you can see that there is a region here where the elements are desynchronized. They have a whole distribution of states. But there is another region here and here. This has a periodic boundary condition, so it's actually an extended region where the elements have the same state. They are synchronized at this moment. And this state is stable. It persists for long times. So they gave to this state the name of chimera states. However, this type of phenomenon was observed earlier by Kuramoto and Batok. This is the same Kuramoto, the famous one. Okay? And in a paper that they called, but they gave a name, you know, a less commercial name. They said coexistence of coherence and incoherence in non-local coupled phase, which is actually what it is. And perhaps because they don't give the right name or the right journal, so this one became known. However, people now recognize that actually the earlier reference was Kuramoto. And later, Abrams, Mirolo, and Strogas studied coupled populations of oscillators. That is, groups of oscillators which are have internal coupling within each group, and also there is coupling between the groups. This is what this describes. And for some conditions, they also observe this type of collective state. Here there is a snapshot of this is one group, one set or group, and this is the other. The elements in this group are all synchronized at this moment. They have the same state, and here they are desynchronized. This is the typical picture of a chimera. And of course, that depends on initial conditions, can change, and it can be one or the other, or the amplitude may change, depends on parameters and distribution of initial conditions. So what is known from the beginning is that the condition for chimera state is the existence of non-local interactions. With local interaction, first neighbors, it doesn't appear so far. So this is what is known. And probably not a lot more. It is an open problem. So many people are intensely working on this type of phenomenon. There is currently much interest in continuous space systems to observe chimeras have been observed in Stuart-Landau coupled oscillators, in complex networks, small worlds, all kinds of networks already have been reported with this type of state. And different type of chimera states have been reported, multiple chimeras, breathing chimeras, dead chimeras, all kinds of things. It has actually been observed experimentally, so it's not just a curiosity. The first experimental observation of chimera state was in a chemical system. That is a system of chemical oscillators. I cannot give you the technical details because I am not a specialist in these things. I will just give you the general idea of the experiments, especially in terms of a review. So this was done by the group of Ken Showalter, and what they have is two globally coupled population of photosensitive chemical oscillators. They have two containers with some fluid, and the oscillators are small spheres covered with the reactive. So it is localized reaction. So it's like a discrete oscillator. And they had in their experiment 20 in one in each container. And there is a global coupling between them because they are photosensitive and they can emit and absorb light. And so the actual equations are very complicated to write because it's a DC reaction, but the scheme of the coupling is like this. I mean, this is the intensity of light in an oscillator in a given group. There are two groups denoted by sigma. And there is a sigma, I sub sigma is the mean intensity of a given group, of the light. And so an oscillator in a given group, sigma, is coupled to its mean intensity and also to the mean intensity of light of the other group. So each one is coupled as an internal coupling and also a coupling with the other group. That is the scheme. The actual equations are very complicated. I mean, on this, probably they have not even been written yet. Okay? But that is the phenomenology. So what they observe is this. Here this is the normalized mean intensity of each population. And this is the mean intensity of, one is in blue and the other in red. And for some parameters, values, they are both out of phase. That is, if you take a snapshot at the given time, you see that all the oscillators in one population, in the blue population, are synchronized, and the others are out of phase, are synchronized but at a different value. There is no direct contact between the two the elements in separated populations. For some other parameter values, you see that they start to desynchronize. One population keeps the synchronization, I mean the intensity is high, I mean that they are in phase, they are synchronized. The other starts to becoming desynchronized. And here you see that one is synchronized and the other is desynchronized. The mean intensity of each looks like this. The synchronized has a high amplitude and the other one looks like this, a small amplitude. This is a chimera state. This is also a chimera state for some parameters. You see that?
In other words, the two populations are identical.
The system is completely symmetrical. There is just that is the interesting thing about this phenomenon. It's a broken symmetry phenomenon. It's a spontaneous. There is there is no a priori configuration for that. Okay, and it's stable. I mean, of course, this is a well-controlled experiment. If you do numerical simulation, you may find that the size of the synchronized region may vary with initial conditions and like that. But the phenomenon is stable. There was another experiment in mechanical systems. It's actually a system of oscillators. You have basically two swings coupled by a spring. It's a general physics experiment. And on each swing, you have metronomes, oscillators. They oscillate, and you can measure the phase of the oscillator. And you can also measure the angle of the swing, which means the mean of the whole system. And with some ultraviolet light, they can measure the position of each oscillator with precision. And what they found, here they represent the phase of the oscillators. I think there are 15 on each swing. So it is also two populations of globally coupled mechanical oscillators. And what you see is that for some, you vary, the parameter here is the coupling, or the spring constant. For some parameter values, they become, the two populations are in phase. That is, they are oscillating all with the same angle. Here is the distribution of angle. Okay? Here, actually, the populations are in different colors. Each element is a point. They are black in one population and red in the other, but here they are all synchronized. They are all in phase and are one on top of the other, and you cannot not see very well the different colors. So here they are in phase. For some parameter values, then you see this phenomenon. You see that a group, let's say the red ones, keep in phase, but the other ones are desynchronized. This is a snapshot, the same thing that we were doing before. For some other couplings, you see that the population become out of phase. The population is here and the others are here. That is, one are becoming like that, the other becoming like that. And for some other parameters, the system becomes completely incoherent. I don't know if you have seen this. I can show you the videos of this stage. If you like, let me see how you do this. Let me show you first the in phase. Okay, this is the synchronized. You're just looking at the oscillator, the light of the oscillators. Okay. Yeah. You see? This is the coherent state. This is out of phase state. Okay? You just see the lights. You don't see the spring, you don't see the swings, because they are just looking at the positions. Okay? Okay. And this is the chimera state. How it looks like. This population is synchronized, and this is the inside. So this is equivalent to the experiment of the chemical system. Okay? We saw before. Okay. I would like to show you another phenomenon that has to do with this. It's related. Okay. That is called unihemispherical sleep. Just to show you how it appears, this phenomenon appears in different contexts. In some species, mammals and birds, sleep, the state of sleep in the brain, is generally associated to two physiological states of the brain that are reflected in an electroencephalogram, which is rapid eye movement and slow waves. That are characteristics of sleep. Unihemispherical sleep is characterized by the presence of slow waves in one hemisphere of the brain and the synchronized activity associated to wakefulness in the other. This is a bird which is undergoing unihemispherical sleep. See, yeah, actually, they sleep with half the brain. I hope that you are not in unihemispherical sleep in my talk. Because some student told me that not only we humans also have this ability. Okay. So it is believed that it is it's considered that this adaptation is an evolutive advantage for this species. It serves as a vigilance for predators, sleeping during migration, especially for migrating birds. Like they can cover very long distance without stopping. So one of the things is how they do that when they sleep. They do that and they switch the brain. Yes. And it's especially important for cetaceans, for whales and dolphins. They do that, and this has been measured. This is an example of unihemispherical sleep in dolphins. It's an electroencephalogram of a dolphin. Here is the electrodes are in one half of the brain and the other, and that is what you see the signals, the electroencephalographic signals. It looks like this. In one hemisphere, you see slow waves of big amplitude. That means that there is some degree of synchronization. They are in phase, so the amplitude is large. The other half of the brain, instead, looks like this, desynchronized. And it switches. So after some time, the one half becomes awake, the other. So it is because they have to breathe. I mean, they cannot fall asleep at all because they will drown. So that is an adaptation. So now, of course, for a physicist, this is a chimera state, and many models of population of neurons have been developed to explain this. This is interpreted as a chimera state. So this chimera state appears in many contexts, and it is believed to be a very general phenomenon. It's just a state of synchronization, something in between order and disorder, complete synchronization and incoherence. It has also been observed, as I will show you, in models of social dynamics, models of interacting social agents. So, by Maxi and collaborators, the model is represents two separated social groups, two populations of social agents, each with its own internal dynamics, just the same of the two systems that we saw before, the mechanical oscillators or the chemical oscillators. The same thing, but with an interaction rule that represents social interaction. Okay. So, but in the context of society, represents two separate social groups, which is own internal dynamics, that get information about each other just through the reciprocal mass media interactions. The elements in one society don't have a direct contact with the element of the other, but they only see the TV of the other society, for example. See? That is a mass media and average information. There is no direct contact between individuals of the different groups. So you have two populations, alpha and beta, of sizes in alpha and beta. The state of an agent in population alpha is given by an F component vector, and each component can take Q values or options. Is the usual axiomatic model that I don't have to explain here. And the global field of population alpha is just the statistical mode. That is, each component of what we call the mass media vector of the population alpha, each component is the most abundant component of all the elements. Represents an average of what is more abundant in population alpha, and the same with beta. So we introduce a parameter B that represents the intensity of the interaction between the global fields and the elements of each group. So this is the configuration. There is no direct contact. They interact between themselves and with the field, the mass media field that's come from the other. The dynamics is very simple. At a given time, you take one element of alpha, one element of beta, and then an element of alpha interacts with a probability B with the mean field, the external mean field, and with probability y minus b with a neighbor. And the same with beta. And then you update the fields. If you interact with the field, they become updated because the interaction modifies the fields. So you see, it's like you see two groups. This is CNN being watched by some people here, and this is, I don't know, Telesur. I hope not. Okay? That is what this represents. That is the idea behind this model, the social motivation that we had when we were doing this. So the interaction consists of the usual interaction in the model for cultural dissemination of Axelrod. If an agent interacts with the field, the probability of interaction is proportional to the fraction of components that they share in their state vectors. And the interaction consists in that the element alpha adopts an shared component of the field beta. The field themselves don't change by interaction. They can affect, but they don't change directly. They change because they represent the average. And there is an agent-agent interaction, internal interaction that is the same. If an agent in alpha interacts with another agent in alpha, the interaction is proportional to the number of components the fractional components that they share. And the interaction consists that the chosen element just copies one of the components of the other neighbor that it doesn't have. That is it. What happens is this. For some parameter, you see, the interaction is zero, that is, you have just two independent populations, you have the usual Axelrod model that if the number of options is below some critical value, each population reaches a homogeneous state. If the number of options for each component is above some critical value, each population reaches a disordered or incoherent state. But now, if you couple the two populations, you have, for different parameter values, you have these main collective states. You have a state where both populations reach the same coherent state. They are in phase. You have, for some other parameters, each population reaches a homogeneous state or coherent state, but different. These are the state of, this is population, the states, the elements are given, the state are represented by a color, and this is time, okay? They are ordered here. And this is time. The state as a function of time, given with the color code, okay? For some parameters, both populations become disordered. And for some parameter, one population becomes ordered or incoherent, or coherence, and the other becomes incoherent. This is the equivalent to a chimera state. We call it a chimera-like, and in the title of the paper, we were very conservative and said, well, like Kuramoto, coherent and incoherent states. However, it has been referred as the first example of chimera state in social dynamics. And people like to refer to this paper just to include the universality of the phenomenon that appears in many systems, including social dynamics. So it's a common phenomenon, appears in many systems with non-local interaction. As you see, all these systems, the common ingredient is non-local interaction or long-range interactions. So chimeras is an open problem. We don't know a lot about why, what is their nature, or how do they arise. Yes?
This is a question for now, for the end, but I will ask it now. I never understood the difference between chimera state and just multi-stability. For example, you know the spatiotemporal intermittency in fluids, you have a turbulent patch
yes.
in a laminar fluid. Is this different? And this is local interactions, as far as I know. So what is the difference between this kind of states and some localized?
The chimera state is a state that is it persists in time. Your concern is my concern too. In fact, what I will show you has to do with your question, okay? But what people call chimera state is something that persists, that is stable. In a fluid, probably spatiotemporal intermittency or this kind of coexistence of laminar and turbulent phases in a fluid, it changes. It's a pattern that changes in time. Probably that will not be called chimera. People will say that chimeras are...
Chimeras and finite size systems are not stable. Never.
Oh yeah, well... I know that work but...
in continuous systems they can be stable, but in for finite size systems, they've been shown to be always transient. It can be very long transients, but they're transient.
Well, I don't know if that is general. Okay? I don't know if that is general because, for example, in this case, how do you get out of this state? In this case, this is an absorbing state. So to get out of here, you have to perturb the system.
And I agree, since there is no common definition of chimera, there is room for different kinds of...
Yes, of course. We are talking about an open problem. Part of the thing is this, I mean, are they stable? How large has to be the system to call it a chimera? And all that, of course. All what you are saying is part of the discussion, okay? But there are examples, for example, in this case, that is an absorbing state, it persists. I mean, there is nothing that you can do to get out of this state. And there are other cases where this happens. So I don't know if that is general, but I know that there are studies about that. There are very long transients, and, okay, of course. However, to solve a problem, you have to go to the source, to the very beginning. And it happens that actually was observed, this phenomenon was observed earlier, and probably was observed for many people, as you said, people may have seen that and didn't make a big deal about it. That is what I suspect, because many people, you and including myself, we saw these things, and well, okay, there is nothing strange about that. But however, what is interesting is that it was observed by Kaneko very early. He was this is a famous paper where Kaneko introduced what was called the globally coupled map lattice. At that time, that was kind of very abstract mathematical thing. People thought that it has nothing to do with reality. And however, it has many ideas, as many of the papers of Kaneko. And what he observed, these are just a system of elements globally coupled in the following way. X of I at time t is the state variable of a map. A map just means that the time is discrete at time t. And then you have the state of this map I at time t plus 1 is a function of its state at that time plus the mean field influence of all the rest of the elements. And the form of the coupling is called diffusive. It's the usual diffusive coupling extended to n neighbors. Okay? So Kaneko was studying this system. Epsilon is the coupling strength to the mean field. He was studying a logistic map, basically. It was an extension of the dynamics of a single map to a spatiotemporal system. Before that, he was studying a coupled map lattice in 1 dimension, then people studying 2 dimensions, and then Kaneko extended to a global system. And what he found was the following. This here, it is represented the time series of a system of 50 elements at that time for different coupling parameters and local parameters of the local map of the maps. Here you have 50 time series, but you see that the 50 time series just fall into 2 signals. That is called 2 clusters. That means that there are 2 groups synchronized, where all the elements are synchronized, but they are not synchronized to each other, the 2 groups. That is called a cluster state. And for different values of parameter, there are a whole variety of clusters. You can have 2, 3, 4 clusters, and with different periods. It is a very rich. This simple system is amazingly complicated. I mean, all the behavior that can show. So cluster, it just occurs when the elements in this system segregate into subsets that can be distinguished such that the elements in each subset are synchronized. This phenomenon. So a single cluster would mean synchronization. All the elements are in the same cluster, in the same set, so they are synchronized. Here, the 50 time series just look like this. It's incoherent. Just 50 signals with no distinguishable pattern. There's just a desynchronized condition. Here, this appears in a figure. Actually, this is in the caption of the figure. Kaneko doesn't make a big deal of it. Probably he was thinking, as you said, so So he says this. He says, this is a partially ordered state where you have one cluster, I think in this case 24 elements, 4 in 1, and the rest, they move like in a cloud of incoherent elements. But this is actually a chimera state. But you see, it's a chimera state, but with no notion of space. It does not localize in space. It's a chimera in time. So the concept of chimera in time now is different than what you were thinking of spatiotemporal or turbulence. Okay? Later, in the last year, in the journal Chaos had a special issue for its 25th anniversary, and Kaneko was invited to write a paper about globally interacting systems, and he says that paper, later he mentioned this. This time he was aware, and he said later, he said this type of state, this kind of mixed state of synchronization and desynchronization was termed chimera state. Okay? So, and doesn't say more. I mean, so, what? Okay, cluster, at the beginning also clusters were thought to be a curiosity. I mean, that it's just maps. Maps are not, people thought they were not real, have to do much with the reality. But however, clusters were observed experimentally in chemical reactions and also in other type of systems, okay, with global coupling. So, we decided to study actually the phenomenon of chimeras and clusters in globally coupled systems, which in our opinion is a simple enough system to study this phenomenon and computationally efficient. You don't have to integrate anything, and simple enough to try to understand a few things. So this is an example. You consider the system of Kaneko, globally coupled, okay, with mean field coupling. And what we put in this case was a local dynamic which had what is called robust chaos. Robust chaos means that the local dynamic has no periodic windows in a range of parameters. It's not like the logistic map that when you move the parameter, the local parameter, it bifurcates and presents windows. Now there is a finite range where there is no windows at all. It is chaotic and purely chaotic. Okay? So it is a robust chaos map, 1-to-1, in the interval 0, 1 to 0, 1, and the parameter was B here, 0 to 1 is robust. The Lyapunov exponent in all this range is logarithm of 2, which is positive. And also it has a Schwarz derivative negative. It doesn't matter now, but I will tell you about this later. Okay, it's a map that was proposed some time ago. So what you see is the following for different parameters. After some transits, you run the system. After some transit, you observe this. Since you don't have a spatial location, you have to introduce one. I mean, you have to call somebody the 1, the 2. So there are many ways to do it. I mean, but in this case, we order from the value, the variable, from the smaller to the largest one, okay? At some given time. After 20,000 iterations, we order them and give a position. The lesser one would be the number 1 and the greater number n. And you keep that order. You give it at 1 at that time, and then you don't touch it anymore. And so you represent time and a position. It's not a real space. It's just the evolution of the space in time. It's not real position, okay? So here, for some parameter, you see that the system is incoherent. Okay, it is 100 here.
So okay. Time is going down?
Time is going down. Here is time. Time and states. See? is a color code. Okay? For some parameter, you see this. The system spontaneously split into one order. Set someone this order. It's going down the time.
No, but horizontally, no.
Horizontally are the states with the color. The I. But the color represents X of I.
Yes.
What I mean?
But they have been ordered afterwards.
Yes. They have been ordered, and then you keep that order. But it's an artificial order. It's just an arbitrary order that you give. Otherwise, you will see the coherence. You don't see the coherence because it will be in any position. So it's just a... Okay. So this is the chimera. So what Kaneko saw was real. It is very stable, by the way. We have this by thousands of iterations. Once it forms, and it is very stable because there is no notion of space. Once it's formed, there is no interaction almost between the system. The subset that forms the cluster, the synchronized cluster, it maintains that itself, and it can stay there for a long time. Okay? Of course, I know that it isn't. It's not general. We don't know exactly. It has not been proved in all systems that chimeras are always stable. But in this system, as far as we know, it is quite stable. At least it lasts for a very long time. For some other parameters, you see two clusters situation, and you can see even more. Here is another situation where you can see a chimera with two clusters. Here there is a cluster, and here there is another cluster, and here is a disordered state going like this. And you can have a coherence or synchronization and a great variety of situations. So to characterize this collective state, we introduce a measure for cluster, the usual. You call that two elements belong to a cluster if their distance is smaller than some threshold.
So what do you change to go for? I guess that you can change anything, but here what you have...
You have two parameters. You have two parameters, the coupling and the local parameter of the map.
So here you change the coupling, for instance?
You can change here I will show you the diagram. You have in the space of parameters you can see the states. We did that characterization, but with some statistical measure. You have to measure the state. So that's what I am doing here. You say that two elements belong to a cluster if their difference belongs to threshold, that is the numerical threshold. You have to give one to define what you call numerically a cluster. Okay? And then you can measure, with this definition, the fraction of elements that belong to some cluster. How many elements are at this distance or are above that distance, and that is called the fraction of elements that belong to some cluster. That can be also calculated. And to distinguish a cluster state from a complete synchronization state, we measure the standard deviation of the instantaneous values and average over time after some transients. It's the average of the standard deviation of the state variables over time. So you can calculate these quantities in average over time as a function of the coupling parameter and the local parameter. So when p equal 1, that means that all the elements are in clusters, and sigma equal to 0, you have synchronization. All elements are in cluster and there is no dispersion, that means they are synchronized. And if p equal 1, but they are all in cluster, but there is a dispersion, it is a cluster state. All the elements are in cluster like this. If the fraction of elements in clusters is between 0 and 1, of course you give a minimum value also to measure what would be the minimum size of cluster that you can measure. It is a chimera state, And if the fraction of elements is clustered in clusters is 0 and the dispersion or the standard deviation is positive, is in incoherent state, you can measure these quantities as a function of the parameter, and that is what you get for this system. See? You see synchronization appears about this value, 0.5, you have clusters, you have a region of chimeras, and you have the incoherent state. Chimeras appear, you see, between clusters and incoherent states. Yes?
When epsilon tends to 0, you still have chimera states.
Epsilon to 0, no, because it's not coupling. It's not coupling.
The limit is clear.
No sigma, B0, no.
Yes.
B.
This is B. No, the sigma, the epsilon 0, yes, sorry. Okay. So, you can characterize in general, well, not in general, but you can make a model of system with global interaction with globally coupled maps. We call the global interaction, we say that the global interaction means, what it means is that all elements in the system are subject to a common influence or a field. That is a global interaction. So as a model, we consider a system, we call it system S, of maps subject to a global interaction field with this type of diffusive coupling. That would be the general globally coupled system with a field that can be external if the dynamics of the field, the field has its own dynamic that doesn't depend on the state of the element. That would be a forcing external field. An autonomous system, an autonomous global field will occur when this global field depends on the state of the element. For example, the mean field, the average that one usually uses, is one example, but it can be anything. In fact, it doesn't have to be, as we have done in other works, it may not depend on all the elements. It doesn't matter. It's just an influence on all the elements that matter. And there is also, in the same context, you can analyze what is called environmental coupling. That is when the global field has its own dynamics, but also has some feedback from the state of the elements. So all this global interaction can be described with one scheme, one framework. There are, in this framework, several collective states of synchronization that you can define. Synchronization occurs when the state of the elements are the same for all the elements. And there are two types of synchronization with this condition. Complete synchronization is when the elements are equal to each other, but also equal to the coupling field, to the global field. And generalized synchronization, when the elements are synchronized among themselves, but not to the global field. This is synchronized or incoherent state is, of course, when the elements are different. A clustered state occurs when the system segregates into K clusters, that is, all the elements are in clusters, K, integer number of clusters. Elements in the He cluster are synchronized, but there is no synchronization among elements from different clusters. You can define the size of a cluster. You can define the fraction of elements in cluster like this. So a cluster state means P equal 1. And when the fraction of elements in cluster is 1, so it's a cluster state. Nothing is left out. When something is left out, you have a chimera state. So a chimera state is the coexistence of clusters plus what is left out. That is 1 minus P times N. To remind you. Okay? It has been shown in a series of work that up to here, these states are equivalent in autonomous or global systems. Okay? That, for example, generalized synchronization was first discovered in driven systems. And then it was shown that it may occur also in autonomous systems, and clusters that were discovered by Kaneko in autonomous systems can also occur in driven systems. It is equivalent because the nature of the field is not important. And in other work, we show that actually it has to do with how much information the global field transfers to the maps, to the local maps. It's a problem of scales. You have a global scale and a local scale. And it can be shown that all these states of synchronization and cluster have different, they can be distinguished. In fact, the information transfer from an autonomous field or an external field, even that their collective states are similar, the information transfer is different. But that is another problem. What we're interested now is in this, in the chimera state. How can we understand the chimera? So when the system is in a chimera state, a system with global interaction, the dynamics is described by this. All the elements in a cluster just become synchronized, so they are represented by a single map. So you have now a reduction of the dimension of the system when it is in a chimera state. You have the elements in a cluster, in cluster He, they have this dynamic, and the rest of the elements that are synchronized have just the normal dynamic. Okay? The incoherent. Again, you can distinguish the complete synchronization state, the incoherent state, the cluster state, the chimera state. They are just special cases of this system. So let's consider as usual, let's consider that the global field is a mean field, an autonomous system. So the dynamics of a chimera state with a mean field can be written like this. That is, these are the incoherent elements, and these are the cluster elements. Okay? What you see is that where P he is the size of the relative size of the cluster, the number of elements in the cluster. You see that the local dynamic of a cluster is modulated by its size, by its relative size. And then you have here the field of the incoherent elements. That actually is like a noise. Because, especially in the case that we are using, that are chaotic maps, this incoherent chaotic map defined between 0 and 1 is just like this. In fact, noise of a small amplitude because they cancel each other. As you saw in all the incoherent parts, you see that they are always the amplitude in this sleeping brain. It's a small amplitude noise. It looks like. Okay, so consider the simplest case of one cluster. A chimera with one cluster, usually. Half and half. Part of the system is synchronized. So the dynamics reduces to this. One cluster and the rest of the elements. It's like this. So the configuration is this. You see, it becomes actually like it's a driving global field, but that receives some feedback, you see, from the elements. This is the configuration. So, as a simple model, as a simple approximation to understand, because once you see this, you say, well, this looks like this is a driver. This is what is producing, skipping the chimera. This is driving the rest of the system. The cluster acts as a global field. So, since one can observe that the field of the incoherent element is looks like noise with a small amplitude, you can make an approximation. Okay, let's think it's like noise, and let's approximate that is almost constant as a first approximation. Try to make a model to understand what are chimeras. So this looks then, if you assume that this is a constant, just looks, now it looks like a driven system. You have an external field that is the dynamics of the cluster acting on the rest of the elements. In fact, the size, now this is a general system, a driven system. So what you see now, if you put the parameters here where in the equivalent autonomous system you saw chimeras, you will see chimeras here too. See, these are the parameters for the chimera that I showed you. This is with the same map with robust chaos that I showed you. So you assign a parameter, a value for the parameter p, and then you see a chimera with that size, approximately. It depends also on, it's sensitive to initial conditions, but not that much. And what you see is this. This is the state of this driven system for the same parameter of the autonomous system. So you can see that the chimera is not just happens in a autonomous system. It may happen just because it's an induced state by a global field acting on the system. There is no difference. It's not because it's a spontaneous, it can be also induced, and it can be equivalent. The same that clusters were shown to be equivalent, the same that generalizing clusters were shown to be equivalent. So you can do now several things. You can see chimera, like you can see this as a single driven map, several realizations, many realizations of a single driven map of an extended system of maps, n maps, subject to an external global field. And what you see is that a fraction of these driven maps, P, gets synchronized and another fraction are desynchronized. I don't have time to show you, but you can also get the chimera, that is a fraction of the map synchronized with the field, and another fraction is not. That is a generalized synchronization state. Chimera can be interpreted as a generalized synchronization state. Okay, you can calculate the condition for synchronization, that is that all these maps synchronize with this, that will be complete synchronization. When you get for this system is that it occurs for synchronization occurs for epsilon greater than 1/2, that is, you remember, is what we got numerically. Oh, where is it? No. Here. Okay. Actually, very recently, there is a report of observation of chimeras and clusters in a globally coupled network, also without the notion of space, by the group of Harsh and Roy. No. I also cannot give you the technical details, but it's a globally coupled system of 4 elements, very simply. I guess it is very difficult to do 100 or 1,000 of these things. I will tell you later an experience with the limit n in experimental system, if you remind me. Okay, so it's basically optoelectronic oscillators, and they have their own internal dynamics, and they are coupled to each other by electrical signals. Okay, and so here are the states for different parameters. You see, there is a state of complete synchronization, all are equal, and so the signal of the 4 oscillator looks like a single one. They're synchronized. Here, there is a state of 2 clusters of 2. So the 4 signals just reduced to 2, the blue ones and the red ones. Here, you have a cluster of 3, so you have the blue ones and the red one alone here. And there is a state, a little chimera of 2, and the other one is probably the minimum chimera that you can be. And probably this system can be treated. We have in that problem. With 4, you probably do the math. Okay? And so, you have these two, and the other two look desynchronized. So, if what we're saying is correct, they can also occur by external forces, can be induced. If these are photosensitive, probably you can do it with an external field. You can, with the right conditions, you can do it. That is basically what we are saying. So let me conclude this talk. And as we said, chimera states are spatiotemporal patterns in network of identical couple oscillators in which you have coexistence of synchronous and asynchronous states. It's an spontaneous broken symmetry state, but it can also be induced. There is much interest now in this type of phenomenon because it has been found in many models, including social dynamics. And it has been found experimentally also in different contexts. There is little known, it's an open problem. What so far we know, what we are more or less sure is that it requires long-range interaction. And they were actually observed by Kaneko long ago in globally coupled systems, so it is worth studying these systems in detail. So we're kind of doing the work that Kaneko didn't do at that time. And probably because he thought it wasn't important. And so has been found in experiments in systems of global interaction. We propose a model for such systems where a global interaction field can be autonomous or external. There are several collective states of synchronization, complete synchronization, generalized synchronization, incoherent state, clusters and chimeras. We can characterize these states in this space of parameters. I think what is important is that cluster and chimeras are associated states. I mean, they are always together. They always appear in systems with global interaction. They are related. They are actually the same thing. I don't know if to say that, but it sounds good. I mean, chimeras are clusters. Okay? In other words, a kind of cluster. And in the case of a chimera with one cluster, one can do a simple model where a system can be described by a driven map, and the dynamic of the cluster acts as a driving field, and you can find states of complete synchronization. Chimera would be a partial synchronization. A cluster would be a generalized synchronization, and this may be useful for various things. I mean, to control prediction of chimera states in autonomous systems. And well, as I hope that you see that it is an interesting problem, and it is open, and there are many lines of research that one can follow. Thank you very much.
Thanks very much, Maya, for this talk with very clear concepts and questions. Yes.
Thanks a lot for this nice overview, in particular highlighting the nice work of Kaneko in that context.
You were familiar with the work?
Yeah.
How?
I have one question that I often ask people working in chimera states. And I would like just to have
I am just a start.
your point of view. And that the target direction, how would you define or what constitutes a chimera state? Because so far the definition is very phenomenological.
Yes.
Allow me to specify the question a bit more. For example, you nicely show the chimeras as in a transition region between the cluster state and the incoherent state.
Yes.
Connecting that with the question of Emilio earlier, what would be the conditions for a chimera to occur? That you have the coexistence of cluster states and an incoherent state, so that both are stable at the same time?
Well,
So
at the same time, because
they could both coexist, or do you require
like a
cluster state
bistable, multi-stable state.
or could the incoherent state only be stable? So what in the case?
Well, in this case, let me tell you. I mean, in this system, this is quite robust. We show. We chose this system because it's very robust. It has a very consistent result. And so what we found is that it is reproducible. Okay? there are cases, especially what Kaneko studied in the logistic map. The logistic map is full of periodic windows. So any small variation can lead you to a window or to chaos, and so it is very, very multi-state. So the region, Kaneko has a phase space like this in his article, you know, and he has this. He draws this. He says clusters of many sizes. He has this, and this he has a region like this, and he says all else, everything else, you know, partially ordered states and all that. And he says that there are a variety of things, probably because he was using the logistic map that is very multi-state.
But it would be
This is quite robust. That is what we use this one for one reason. The other was this that I didn't mention,
but that does not
also we
answer the
didn't want to
question.
make a big deal of it.
But that doesn't answer the question whether at the same time, for example, the incoherent state, the fully incoherent state, and the fully coherent cluster state would be coexisting with it.
For different initial conditions, you mean?
For different initial
For
conditions.
example,
We
if
didn't-
you start with a cluster, go down in epsilon, where is the transition to coherent or to chimera?
Right.
So you start
To
in
chimeras, to chimeras. I mean,
To
if you move like this is quite consistent. I mean, this state is real.
You see the two
It's
lines.
real. Of course, the border or the transition line
Depends on initial conditions.
may, but it is there. It is there. There is a region, a clear region of chimera states.
Sure, but if in a region where you have chimera state, you
There
definitely
may be,
have coexisting
yes,
state of a fully
in
coherent
the boundary.
Yeah, you might have coexisting coherent
Yes.
state, or you might even have
Yes.
coexisting both states.
Yes, it is so. And we saw that for some realizations, for some parameter values close to the boundaries, you see that. In the driven map model, you see that for the same, you put the same parameter and you vary the condition. Not only that, it may vary the size of the cluster state. It may vary with the initial condition. We know that. But it's quite consistent in the sense that it is real, it is there. But of course, the boundary is not well defined.
I'm sure you will continue discussing.
Yes.
More questions or comments? Really?
You have promised to say something about the limit of n in experiments.
Oh, I don't know because this is being transmitted on TV.
Okay.
No, but no, it's not the.
Censorship.
No, let me. I will tell you that since you asked me, and you want to be rude. You see that this experiment for John Hudson. It happens that I was at the conference. Actually, was at the ICTP at Trieste about that year, I guess, or 2001, or I think the same year. It happens that Kaneko was in the audience, and I was there. It was very young at that time, and it was, the announcement of the cluster that Kaneko found. And so. But Kaneko is very shy. I don't know, it's a person. And after John Hudson explained the finding of Kaneko, he said, well, this is what Professor Kaneko found, and so on. You would like to say something, Professor Kaneko, and he said, why his system was 64 chemical oscillators, coupled globally through in parallel. It was a parallel resistance system, so it was a kind of global coupling. So he asked, why did you do such a small system, 64? Why don't you do 1,000? That was his question. And so Professor Hudson said, Professor Kaneko, it seems that you're having a long time, you don't go into the lab. So not a good squad. Because you may think, this system of four, just this experiment of Rahashirol that I showed you, why did you do four? My students said, why did you do four?
But that was in order to have a minimum motif that allows for
Yeah.
chimeras.
Yeah. Probably they can do more than that, but not 1,000.
Any further questions? If not, I think we should stop here. Mario is going to be here until Wednesday next week, including Wednesday, so for a few days. So I'm sure he will be happy to discuss with any of his interests.